Hello from the College of Worcester in Worcester, Ohio. I'm going to be talking about passive samplers for PFAS compounds. Just to recognize other people on the project team, Dr. Craig Devine, Eric and Cotter, Kevin Toth are all Arcadis, and we've been teaming up to work on this project. Helping me in the lab are undergraduate students here at Worcester, Heather, Riley, and Noah, and the funding is provided by CERTUP. A passive sampler is a device that would be placed in the environment that accumulates analytes over time, returned back to the lab and measured to understand the concentration of those analytes in the environment. Compared to a traditional grab sample, now, a passive sampler can have a lower cost because of reduced shipping, like weight of the water, and including limiting site investigation waste. It also can provide a time-weighted average concentration and work across diverse sampling regimes like surface and stormwater. So those are some of the advantages. Let's talk about the passive sampler design itself for PFAS. Okay, this design that we have come up with is relatively simple. It's about a 5 by 2 centimeter polyethylene tab that contains a granular absorbent behind a mesh screen. So there's no diffusive barrier to the accumulation of the analyte because the granular material is direct contact with the water. So this allows for a fast sampling rate. The granular absorbent is specially designed to absorb PFAS in that it has a hydrophobic component mixed with a weak ion exchange resin. To help the binding of short chain PFASs, copper ions are added, which have the added benefit of being a biocide to reduce biofilm absorption. The device fits it within a 50 ml Falcon tube for easy recovery and shipping, and is pre-wetted, so it just drops right into the water upon receipt into the field. You have attachments that could go either hang it because it floats or can be weighted to be synced to the bottom of a sampling zone. After the sampler is returned to the laboratory in the centrifuge tube, it's placed in water that contains surrogates. These are isotopically labeled standards that are traditionally used in like EPA or DOE sampling regimes. After those surrogates have been quantitatively bound after about 8 hours, then methanol is added to release and desorb the PFAS compounds and their surrogates. The methanol can then be evaporated necessary and reconstituted and run by LCMS by the standard methods that are available to labs to run and measure PFAS compounds. In this way, the sampler fits along with very similar with the work streams that are currently used for the standardized methods to measure PFAS. How is that mass absorbed then converted into an aqueous phase concentration? Well, since this is an integrative sampler, there's a certain specific sampling rate that occurs in that system. So that sampling rate is then multiplied by how long it's been there and times the aqueous phase concentration to get that mass that was absorbed, which is what is actually measured in the laboratory. So the key thing that's needed in doing this conversion is to know the sampling rate, the RS value. Those are measured in the laboratory under a variety of conditions for different chain lengths of PFASs. And then there's a lookup table that then is just a constant that's applied into this equation. And so these have been measured across various aqueous phase conditions with different ions, temperatures, and flow rates. Now, one of the really important things we wanted to do in the design is create a passive sampler that was truly integrative, that would give a time-weighted average rather than an equilibrium point. And to demonstrate this, we have a experiment here that was done in a lab in a flowing stream of simulated groundwater, where for most of the time, between 0 and 220 hours, the concentration was relatively low, 100 nanograms per liter. But over one day, the concentration of the PFAS was spiked up to 10,000 nanograms per liter. So there was this high concentration event. Now, if there was an integrative response, that concentration would be accumulated within the sampler and not released over time. So it wouldn't come back to equilibrium when the low concentration was resumed. And this is what we tested. And what we found is that the response of the sampler was an integrated result, and that is that this concentration didn't back diffuse out of the system, but rather stayed accumulated in the device so that the mass accumulated at that specific time matched what was predicted if it was truly integrative. So what this means is that if it's deployed within the field, then this would, as concentrations go up and down, it would act sort of like flypaper then and capture PFAS compounds in a fairly rapid way and deliver a time-weighted response. So after doing multiple experiments, different deployments, we have different options for how these can be used. The most traditional, or we think the best approach, is to do a 2-week deployment, 14 days in the water, that gives a limited detection of about 10 nanograms per liter. However, there's other options that could involve a quick soak or a dip and pull. These could be good if time on site's limited or trying to measure short duration events like stormwater. However, if lower limits detection, are needed, then longer term deployments are possible, thus accumulating more molecules over that time and lowering detection limits. We tested these passive samplers at DoD sites, one at Ellsworth Air Force Base. This was a surface water site where there is something resembling like a stream, kind of like a ditch at the end of the runway, where there is nearby a AFFF fire fighting zone. And that was tested at two different times. For groundwater, that was tested at Peterson Air Force Base in Colorado, where they were put into traditional groundwater sampling wells. So these are some of the tests for the field results. In combination with the passive samplers, GRAB samplers were taken concurrently with that sampling time frame and measured using the standard aqueous phase techniques, EPA 537, and then compared to the results obtained by the passive sampler. And so what is here is that the GRAB sampling concentrations are plotted against the passive sampling results, with the 1-to-1 line going up and down the middle. What we found is that there's a good 1-to-1 correspondence over 5+ orders of magnitude within the Peterson Air Force site. This is a good site because it is groundwater, so it is fairly consistent over time. And so these have pretty good results in comparisons. At the same type of experimental strategy was deployed at Ellsworth Air Force Base. So this is a picture here up on the upper left of the stream. The stream is actually ethereal. The amount of water flow varies by 50% over the course of a day due to the water uptake by the nearby vegetation. So there's a little bit more scatter between the 1-to-1 plots here, GRAB sampling versus passive sampling. But this might have more to do with the GRAB sample being only done once per day, where the passive samplers were being deployed over a longer period of time and trying to capture that time-weighted average. We are currently waiting for the snow to melt in South Dakota, where Ellsworth is, so we can do our second event. And at that time, we're actually going to deploy an auto sampler that will collect more GRAB samples over the deployment event to really verify if that's the case. Are we seeing a time-weighted average over the duration? And just one more piece of data before we finish here. I wanted to compare some of the analytical results that we see if you're an analytical chemist. A traditional way of measuring these compounds is with solid phase extraction, with like an Oasis wax cartridge followed by chromatography. And this is the passive sampler. So these are the same sample site, one with the traditional GRAB sample with solid phase extraction, upper plot down below the chromatogram for the passive sampler, and they resemble each other very much. So this over a 2-week deployment period, a passive sampler basically matches what a 250 mil GRAB sample results would look like analytically chromatographically for comparison. All right, what's up next? Well, we're continuing to field test our samplers, and in the lab, continue to refine our lookup table for our sampling rate measurements. We're transitioning this to a manufacturing company and handing over the SOPs to commercial entities so these can be deployed more widely. In addition, we're also looking maybe for additional field trials in the summer. And if you want an example of the passive sampler, please let me know. My email's there. Thanks.
Yep, we have time for, we have about 4.5 minutes for questions, and reminder to post your questions in the Q&A.
Okay. Could you take a grab sample and then set the passive sampler for 2 weeks?
Inside the grab sampler? Is that what you're saying?
Yes.
Yes. Yeah.
Okay. For long-term deployments, how does biofilm formation come into play? Could it enhance the PFAS absorption?
Yeah, so biofilm formation is definitely something that is unwanted because it leads to variability in the sampling rate, either as enhancing it or providing a barrier to it. Now, our sampling design is trying to make it more resilient to biofilms by 2 reasons. One, there's no membrane there, it's just a mesh material, so water can actually move through it fairly straightforwardly. Also, the addition of copper to the absorbent particles is biocidal and prevents it. So far, even deployments up to several months, we haven't seen a significant biofilm formation, and that's something we're trying to eliminate. It's a great question.
This is really neat. Do you think this would really be feasible for very short contact time situations like stormwater, as you've mentioned?
Yeah, exactly. Like that's one of the things we want to do this summer is set up for stormwater. We have done some ad hoc experiments that are not controlled enough to be really shown here, but because it's going in direct contact with the water, it's pre-wetted and ready to go. We think that it can be used for stormwater if the duration is somewhere around half an hour.
Is this sampler a method that is EPA approved?
No, I don't think there's not an EPA method for passive samplers for PFAS yet.
I was actually curious if you have a cost estimate for what the passive sampler kit might cost.
Yes, it's on one of the slides, $20 a sampler.
Oh, okay. Sorry about that. I missed that.
Yeah, no, it's okay. It was in really small font. Well, thanks for the good questions. If there is any additional information or you'd like to see a sampler or have an example copy, please reach out to me at my email. I'll be more than happy to facilitate that.
Actually, we did have one last minute question. Are you trying any other contaminants with the passive sampler?
Oh, that's a really good question. Are we trying other contaminants? Not we could, but right now our focus, especially with the direction of CERTUP to direct our efforts, has been really exclusively on PFAS. I would say that you could switch out the absorbent design and go after other aqueous phase analytes probably equally as well. It's something to think about in the future. It's a really great question.